Hey everyone, in this video I want to talk about confidential computing. And there are a number of different confidential computing options available in Azure. So in this video I want to look at, well, what are the options, what's the difference between them, and why I might use them. As always, if this is useful, please go ahead and like and subscribe and hit the bell icon to get notified of new updates. Now when I think of confidential computing, there's really a set of steps for the options. So I can think about, hey, there's 3 big steps for the different confidential computing options available to us. And what really happens is as we go up the steps, we gain confidentiality, we gain maybe additional integrity controls. However, it may also mean additional considerations, maybe even app changes to be able to utilize those technologies. So I think about that first step in terms of this, and I did a video on this a few weeks ago, and that is the trusted launch capability. So I think about trusted launch. Now this is built on top of the Generation V2 virtual machines. So we have the Gen 2 VMs and that virtual trusted platform module, the VTPM. So those Generation 2 virtual machines, they're UEFI based. So instead of a BIOS, I have that UEFI. It gives me a number of capabilities, but one of the big ones is that virtual trusted platform module, along with the TPM 2.0 specification. And now what I can do is when I create the virtual machine, this enables me to have a trusted launch VM. If we actually go and look at this quickly, and again, I covered this in detail in the separate video, but if I just go to my virtual machines, I want to create a virtual machine, what I'll see are different options. Now I'm just going to change this super quick to West US because I know I've got all of the options there. And what we have is this security type. So the security type option. And with a Gen 2, well, I can set this to a trusted launch virtual machine. And straight away, it's kind of telling me about some of the capabilities I'm going to get with that. But if I select that trusted launch, I can additionally configure security features. And the big ones this gives me is, hey, I'm going to turn on the virtual TPM, which lets me do the secure boot. So those are the big options around that. And there are particular images that I can leverage. So for the image type, if I select all images, and then what I can do to this is add a filter. So I'm going to go ahead and for my security type, I'm going to select this and I'm going to change this to trusted launch. So then I will see all of the images that support trusted launch. Now the whole point of that trusted launch is it gives me protection primarily against the idea of rootkits. So with trusted launch, the bad thing that I get protection from are rootkits. So by enabling trusted launch, and it's really that secure boot technology, hey, I get protection against that bad thing. So that could be a rootkit that is, for example, trying to get between the UEFI and the bootloader. It could be a kernel rootkit. It could be a driver rootkit. What Secure Boot gives me is that integrity check and a measured progress from the UEFI all the way through to the booted operating system. So this is a great feature. There's not a lot really I have to do to get this. Hey, I just make sure it's a Gen 2, and then I say, yeah, I want trusted launch. But what about beyond that? I'm thinking about steps beyond just trusted launch. Because there are other types of attack. There are other types of trust that I'm relying on. Trust in the hypervisor, trust in the control plane, trust in the administrators at Azure, trust in my own administrators, trust in other things inside my operating system. So what can we do to start not trusting those things? We always think about encryption. I think about encryption at rest. For a storage account, that's just a standard thing. I could use my own key or a platform managed key. For databases, there's things like transparent database encryption. There's different options to encrypt at rest. And then encrypt in transit, we often use TLS. We encrypt the communications over the wire. But what about actually thinking about encrypt the data in use? So if I have, hey, these additional steps that we're going to go to, the next thing I actually think about is this whole set of confidential computing. And this is all about the idea of I want encryption and integrity checking about data in use. That could be the data in memory. It could be the data in the processor state. I want to encrypt that. And there's different levels we think about actually having this, because again, I can't 100% always rely on the provider. I want some additional checks. So this is all about protecting the data when it's being used in the memory, during the computations. And there are two steps to how I can get this. Now the first step, let's go to a different color. Our first step is confidential virtual machines. And we'll see these as these DC A series and also an EC. Should be a big A. Let's just correct that. It's a big C there. So we have these two versions. As we know, the D is kind of a general compute option. The E is those memory intensive options. Now with these are built on AMD. So from a technology perspective, they're still Gen 2. They still have a virtual TPM. But now they're using the AMD processors. I think it's the AMD EPYC 3rd generation. So these are leveraging AMD. And it's two technologies. It's the SEV SNP. So that is the secure encrypted virtualization and then secure nested paging. We often talk about nested page tables with virtualization. So this is a basic encrypted version of that. And what these things together give me is a protection of the virtual machine by having a trusted environment and also an integrity assurance. The key concept of these technologies is the idea that if I have something in that virtual machine write to a memory address, when I read it back, it's going to be that last value I wrote. It can only be that value, or I'm going to get an exception. Now this holds even if that memory is swapped out to disk, for example. It's also going to AES encrypt that memory when it's stored in the memory. The processor registry state is also going to be encrypted. And there are other types of protection as well. Now, if I think about layers, with this AMD SEV and SNP technology, only two things are considered trustworthy. It's only going to trust the AMD hardware and firmware, and then this SEV SNP enabled virtual machine. Everything in between those two things, we've got the AMD hardware, and then you have, well, I have the BIOS, device drivers, hypervisor management, and then the VM. None of those things in between are trusted. It's just that AMD hardware and firmware and the virtual machine. Now, because of this, there are specific images, because there are changes inside the operating system to just support some of these integrity checks. Because when I think about what's happening is the VM is fully encrypted at runtime. This gives me that promise of confidential computing, even when it's in use. There's a dedicated, basically secure processor for the virtual machine. And what this means is even from the Azure control plane, even from the hypervisor, I have protection. So if I think about, well, what are the possible bad things that could happen to me here? Well, from a service perspective, the control plane, for example, if I think about the hypervisor, bad things can happen in the hypervisor. Very unlikely, but there we are. Data center admins. This is giving me protection from all of these things, plus rootkits. So it's building on top of the protections that we had in the previous layer as well. So I'm getting all of those benefits. And we can see these. So if we quickly jump back over to the demo, let's go and look. So I'm going to drop out this marketplace for a second. And if I go back, and this time, the security type, well, I actually want confidential virtual machines. So I'm picking this option now. So I'm going to go to confidential virtual machines. Now what we see is if we look at the sizes, it's erroring. This is not compatible. So I'm going to see all sizes. And what I'm going to do is add a filter. And my filter type is going to be family. And I'm going to enable only confidential compute. So I'm creating this filter. So I'm only going to see confidential compute type virtual machine SKUs. Now there are two different types within here, and I'm going to point these out. If I do that, and straight away it changes. We can see the DC, so that's general purpose workloads, and then there's an EC. And what I'm focused on here is you'll see all of the EC, they're all EC something A. So the A is kind of this AMD. On the DC, we'll see ones that are A and then ones that are not A. Ignore the non-A ones for now. They're being used for other things. And we'll actually see that when I change some other things about the detail. But these are all kind of these A series. We see there's different sizes still within these, but these are those particular SKUs around the confidential compute. Now notice also the images. Hey, this doesn't work. So once again, I'm going to go to see all images, and then my security type, well, I'm going to change that to confidential computing images. Let's try and change that again. There we go. And what we're seeing now, well, this is Windows Server. And for Windows Server, we see there's a 2019 and a 2022. And then we have Ubuntu 20.04. So in terms of the operating system supported in this, today it's Ubuntu 20.04, and then the two versions of Windows Server. So if I think about, okay, this AMD technology, we have these DCA for general purpose and ECA for memory intensive. So it is a special image. So I have to have that consideration. So it's a special image. And today it is that Ubuntu, and it's my Windows Server 2019 and 2022. That might change over time, and it's really because these images have to support the secure mounting, the attestation, optionally full disk encryption, and isolation from the underlying cloud infrastructure. So they're all key things I have to do. But the huge part of these types of virtual machines is there's no app change. My application is completely, pretty much unaware of this. Yes, the image is special to support those things I just talked about, but I can lift and shift my app. If my app today works on Ubuntu 20 and Windows Server 2019 or 2022, I create one of these virtual machines that has those special configurations to support the confidential compute, but my app will just run. Inside the guest operating system, it's just a regular environment. My app doesn't have to have any special changes to run in this encrypted environment. So that's a fantastic thing about this. Inside the OS, my app just runs as usual. So there's no special things I have to do. There might be a tiny performance difference today. Again, at the time of recording, this is in preview. but I think it's very negligible. There is an attestation going on here though. So there are checks that can be asked for about the state of this measured confidential compute. I know as something running inside here, I'm running inside a confidential virtual machine. Optionally, I could select to encrypt the OS disk of this virtual machine and then only be able to decrypt it by having an attestation from the platform that I am running inside. The disk is attached to a confidential virtual machine. And only then with that attestation would the OS disk encryption key be able to be unlocked from Azure Key Vault because it's being tied to the virtual TPM and that attestation. So I can't take the disk and plug it into something else. They're all tied together. The encryption of the OS disk, if I choose to do that, can be tied to the fact, hey, it is this confidential virtual machine. I need the attestation to unlock from Azure Key Vault the key that's being used to decrypt all of this. So I can bring all of those things together. It's crazy powerful. Now, because of these special configurations and the way this works with this integrity, there are some limitations today. So if we go and look at the sizes support are the DCA and the ECA series. It only supports those two operating systems today. It's only in certain regions, but these features of Azure will not work. So I'm not going to go through all of these. They're in the description below, but there's quite a few things. Batch, backup, ASR, dedicated host, etc. You can read through this list. There's a lot of things that won't work today because I've got this special always encrypted type environment. So just be aware that while my application, sure, I can just take and it will run without any modifications, it doesn't mean every other Azure service would still be available to me. Now, what was missing from this set of protection? Well, really, when I think about it, sure, I've protected from everything outside of the guest operating system. I'm protected from rootkits. I'm protected from the control plane of Azure. I'm protected from the hypervisor. I'm protected from the data center admins. But inside the operating system, if I'm in the OS, this doesn't give me any protection, anything. So there's still the risk here of, well, bad things in the OS. Some piece of malware, some process, some VM admin. And by VM admin, I mean an admin within the OS itself. So someone who has administrative rights inside that guest operating system. This does not protect me from those risks. So the final level up is thinking about, yes, I'm still going to get all of these protections that we talked about here and these, so rootkits, service, hypervisor, data center admins, but now I'm also going to get protection from other things in the same OS, and even if I'm an administrator inside the OS, we're going to have protection from those as well. And the way this is going to work is this is all about enclaves. So I'm going to create these protected areas of memory, working with the processor, that's going to be tied to a specific application. Only it can see that memory. Even if I'm an administrator in the guest OS, I would not be able to dump out the memory or interfere with the memory of a process that's using these enclaves. So this is built on top of the Intel SGX functionality. So that's a software guard extensions. And these are the DC series virtual machines. There's no A, so this is the DC series. So this is giving me complete protection, even from other processes running inside the operating system. So once again, this is built on Gen 2 and the virtual TPM. Now, what is different this time is I can think of those layers. So remember, I talked before about the host, the CPU. Well, how does this work then? How can this thing function? So what I'm going to think now about is the idea, well, right, there's the host, there's the physical box. I can think about there's the CPU, I can think, well, there's a hypervisor, there's an operating system, and then there's my SGX integrated application. And if I want to be protected from even the hypervisor and the admins and people in the operating system, there's a protected path directly between the app and the CPU. So this is a locked down communication. And this is going to work today with a number of different Linux. It's really Ubuntu and Windows distributions, different versions of this. Now, because the app is working with these enclaves, this is not a no app change scenario. This is absolutely, I need to change my app. So my app has to be written. I don't have to directly interact with the enclaves. There are a number of different libraries out there. So I'm going to pick a particular library to work with. OpenEnclave.io is an example open source SDK that extracts away the enclave and makes it easier for me to write my application, eases the application development to be able to use those enclave technologies. So I'm probably going to use, there are different ones out there, but I'm going to use those libraries. But the big deal here is, yes, there are code changes. I cannot just take my app as is and it magically uses the enclave. So the AMD option, where it's the entire VM is encrypted, I can just take my app, lift and shift, and run it, and there, I'm good to go. If I want to use the enclave, I have to be working with the enclave. I have to use one of those libraries and change my application to work with some library I'm going to pick to work with. So it's some code changes. But when I do that, I now get that additional protection from other things running inside the operating system. Could be other processes, could be administrators within the OS. If I try to dump out the memory, I just don't see anything. I cannot access the memory for an application that's using those enclaves. Now, there are currently two different versions of these. If we jump back over and take a look, what we see, so I'm going to actually back out of this. Let's close this out. So I'm going to turn this off, just change it back to standard. And now if I see all sizes, I want to add that filter back again. For I still want a family of confidential compute. Remember, I changed the security type to none of them. So now when I look at DC, now I see a whole bunch of them that don't have the A. So these are the Intel-based solutions. You notice I see the AMD ones as well. Ignore the AMD ones. But if it doesn't have the A, that's where it's the Intel SGX-enabled ones. So they're still confidential compute, but here I'm using the enclave. And once again, there's a whole bunch of different sizes for these that I can leverage. Note, there is not an EC. There is not a memory focused version of this. Now, there are two versions of the DC. You can see right here, there's a V2 and a V3. So what happened is the V2 versions, it used the Intel Coffee Lake processor, and there was a maximum amount of 168 megabytes of encrypted memory. So remember, this is the data kept inside the actual memory. And 168 megabytes may not seem like a huge amount, but if I'm doing good garbage cleanup, that's actually still quite a lot of memory. But the V3 actually increased that to 1,500 times the encrypted memory. So it actually goes up to 256 gigabytes now. So if we look at those SKUs, let's actually come over here. So if we look at those SKUs in detail, actually, let me show the old versions first. So this is the V2. And if we look at the different SKUs, it shows us the amount of encrypted memory. It goes up to 168 megabytes for those. If I look at the V3, and do note, it is generation 2 only, and there's no accelerated networking on these. You'll also notice things like hyper-threading is not supported on these SKUs. If I go to the V3, you'll still see it's not hyper-threading. We will see accelerated networking is now supported. So we can see they've called that out. It obviously still is a Gen 2. Notice trusted launch is currently not supported, but is coming soon. So right now I cannot turn on that security option of trusted launch, but it's going to be there pretty soon. But now that amount of encrypted memory is now changed to gigabytes instead of the megabytes. And it goes all the way up to 256 gigabytes now. So a huge amount more of that encrypted memory I can use for these virtual machines. And there's not even an extra premium I pay for these. There's not an additional cost. The equivalent size VM with the Intel SGX or without is the same price. So remember, I'm going to use this for when I need the most confidentiality. Hey, I don't even trust other things inside the operating system. I don't even trust the administrators of that operating system. I need to protect from everyone. And once again, and I'll talk about this, there's an attestation available to me. Say, hey, yes, my process, I'm only going to run in an enclave environment. I can get a measurement all the way down to the silicon that, yes, I have this integrity running. And I might write processes, and there's a big case study about Signal, where it only runs in the encrypted memory. The data is stored nowhere else. It's only stored in the encrypted memory. Imagine a scenario of you had banks wanting to do fraud protection together, but didn't want to make sure the data maybe about the customers was shared. Well, it only would run in that encrypted memory. They can bring that data together in an enclave, run machine learning on it, but no one could actually see the data itself. I couldn't see another bank's data. It's a way to completely move that. Now, once again, I cannot lift and shift my app because I have to make the changes to use that enclave. I can use this with AKS, so I can create confidential pods running on these DC v3 nodes. There's a little special wrapper I can use for this. So we have the 3 layers. Hey, I just want some assurance that there aren't rootkits involved. Trusted launch gives me that. I want protection. I don't trust Azure. I want integrity and I want encryption away from the control planes of Azure, the hypervisor, admins, data center admins. That's the confidential virtual machines, the AMD based. I can lift and shift my application because there's no app changes, but there are special images. I could create my own image based on one of theirs, but I can't just take a regular image and use it. There's special items within the images. Hey, I don't even trust other things in the OS or the OS administrators. Well, I can use enclaves. I can't lift and shift my app. I have to change my application to use the libraries that abstract the enclaves. And there's different types of enclaves, but here we're focused on SGX to get that additional level of encryption and integrity from other things that could be going on. Now, one of the words I've said a few times as part of this was attestation. So what is that all about? So one of the services we have is Azure Attestation. Because it's important, if I'm running, hey, maybe I'm just using trusted launch. Well, I want to know, hey, I actually have that measurement from all the way up from the UEFI, from my OS, that hey, I really have that integrity. There's measurements done. I have assurances from there that, yes, I'm running in this environment. I could think about, hey, I'm using these confidential virtual machines. And remember, we talked about I could encrypt the OS disk for these confidential VMs, and only if I meet attestation, I am running in a confidential VM, should the Azure Key Vault be there to unlock the virtual TPM to get the keys to unlock the disk. Well, Azure Attestation does that. it also lets me, for things like the SGS enclave, to confirm, yes, I'm running in the enclave. Only then will this process actually run. So it's taking evidence from all of the different entities involved all the way up, turns them into a set of claims, and then I provide that as a cryptographic proof to the environment. It confirms the posture of the virtual machine. So this attestation service is what enables me to actually know, hey, yeah, I am running in this nice, secure environment. There wasn't anything that got in the way. It's giving me that proof of the security, the integrity posture of my environment. And that's really a key part of this. So that's it. So that's the whole point of these confidential compute offerings. Hey, I just want protection from rootkits. I turn on trusted launch, Gen 2 VM, virtual TPM, secure boot. Hey, I want additional protection from Azure, essentially. I don't trust it. Services, hypervisor, data center admins, confidential VMs. I get that. Don't have to change my app. I don't trust things inside my VM, the enclaves. Other things in the OS, VM admin, guest admins, can't see the stuff. Azure Attestation gives me the proof that I really am running in this nice, secure, measured environment. There are other advances coming. There's huge amounts of work going on in here. You could kind of think about the day where maybe all VMs become confidential virtual machines. Everything just has that. So nothing ever relies on those kind of trusts. NVIDIA GPUs, I saw an announcement that they're going to have encryption in the GPU, and from the CPU to the GPU have an encrypted path between them. So now if I think about high performance computing, machine learning, training type scenarios where GPUs are leveraged, I'll still be able to have that confidential computing by using those NVIDIA technologies to carry on this idea of confidential computing beyond just the CPU and memory to now those GPUs as well. But that was it. I hope this kind of clears up the difference between them and what they are and what's required to use them. Until next video, take care.